Hello, I'm Aramis, and I'll be giving a presentation about my project and also a bit about the agricultural robot project that we're currently working on in our robotics lab at American Heritage. So to start, I'll give a bit of a background for my project. So in the field of robotics, there are a lot of sensors that are used in just about every mobile robot and static stationary robots. And typically, a robot will collect data from its sensors throughout its entire runtime, and most robots tend to be used more than once. They're not just one-time use tools. So you end up with large volumes of data, and if you want to use this data effectively, you have to have a way to analyze it. So this is where HPCC systems comes in. It can process big data, and it does that really well. However, you need a good way to ingest the data from these sensors. So that's where my project comes in. It provides an API for ingesting data into HPCC systems, and it's open source and it's available to anyone who needs it. So before we get into the bulk of the presentation, I'd like to raise a quick poll. Have you ever worked with the Robot Operating System, abbreviated as ROS? It's a software platform that's used in many different robots across many fields, and it's also used in the agricultural robot, which shouldn't end in the next slide. So to collect data for testing, the developments of my project, I've been using sensors in the lab that also are going to be used in this agricultural robot. And I've mentioned it a few times earlier. It's a robot that's going to collect soil samples and other data inside a field. It's going to collect data from GNSS receivers, so it'll be kind of like the GPS coordinates you get on your phone. A scanning rangefinder, infrared cameras, samples, and it'll also be open source and will involve data analysis. It's going to autonomously drive down rows in a produce field and collect data from the sensors listed in the previous slide. And there's also a virtual reality component, but that's not as related to data, so I won't go too deep into that. Here you can see a few pictures of it. This is taken last week. It consists of two identical chassis linked to each other, one leading and one acting as a trailer. So in my project, I'm covering a few different types of sensors, most of which are listed slides ago. So here's an example of this data. If you look to the right, you can see a small visualization I made. It's has the points returned from the GNSS sensor, and they're linked together based on their timestamp. So you can see that it's really chaotic in a bit, and that the location floats around, even though, as you can see in the picture to the left, I'm standing still. So one benefit from being able to analyze the data on a large scale is that you can apply different algorithms and other techniques to this really noisy GPS data to help determine the true position of the antenna. So if you look here, the GNSS sensor I used to collect this data was the SwiftNav Pixie. It's a module we're using in the agricultural robot, and I had it on hand, so I made use of that. And with my project, I was able to collect data from the sensor after it was published through Robot Operating System. I went to ECL Watch, used the ECL modules I wrote for the project to process the records and also index them. So if you look at the image below, you can see the record structure of the GNSS data. Next is data analysis. So the big data you might collect from robots will include GNSS coordinates, images from cameras. Those tend to be quite large, and also point clouds from scanning rangefinders, which may contain even millions of points. So some of the most common applications of this data would be applying machine learning algorithms to the data collected. And as you might have seen in Robert's presentation, machine learning typically uses lots of data, so it benefits from being done in HPCC systems where it'll be much faster than running it on a single computer. And you could even take the computed weights and biases from the machine learning algorithms and run them locally on the robot to perform the classification or regression in real time. Next is the infrared camera. So if you look at the picture here, it's just a single frame from an infrared camera taken during development. What's pictured is a robot chassis. If you look to the area with most of the heat, that's just the processor. So you can kind of see this is what's going to be received by the robot. This was taken with a FLIR C2 infrared camera. And the way I did this was I wrote a package in ROS that used OpenCV to read the images. OpenCV is a open source image processing library. And then I used two more open source ROS packages to the images into messages, which I then gave to the ROS package I'm writing as part of my project to ingest it into HPCC systems. This is the resulting logical file. So one reason it's helpful to have this available for camera data is that if you look to the record size, for just 593 records, that's probably a few minutes of video. It's taken 136 megabytes. So with a robot that runs for much longer than 2 minutes, this can get really large, and it benefits a lot from having it available on HPCC systems. As for publishing the project, there's a repository containing the ROS workspace, and with ROS you can use C++ or Python to create your packages, and there's also a subdirectory inside the workspace containing all of the ETL modules I wrote. So this is just an example of some of the code that you might write in ROS. This is the Python implementation of the code used to convert the laser scan messages from a scanning rangefinder into something that can grade into through ECL Watch. And here's an example of my layouts used in ECL to contain the records for all of the sensors that I implemented. So before we end, I'd like to raise another quick poll. What roles do you see HPCC systems filling in the field of robotics? So finally, analyzing data isn't in the scope of this project. We're mainly dealing in collecting the data and having it available for analysis. However, it would make for a good continuation of this project. For example, collection of data from the agricultural robot or some other robots that make use of this project, and then conducting the analysis of the data and possibly porting that analysis from HPCC systems to a local machine robot. And thank you.
All right, Aramis, thank you so much. I just want to make sure that everybody on the webcast today noticed that Aramis is a high school student, so we're actually very impressed with your results, Aramis. All right, so I'm going to take a moment. I'm going to review your first poll question. While I do that, take a look at some of the questions that are coming in and prioritize those for us. People in the audience, if you have questions for Aramis, please send those in so that he can take a moment to review those. All right, so on to the first poll question. It was, have you ever worked with a robot operating system, ROS, the platform driving many robots in education, research, and industry? So right now it looks like 80% said they haven't, and 10% said that they have not heard of it. So 10% if you have. So that's awesome. We're glad that our community is getting involved with some of the robots there's so many amazing ones that are out there today. All right, Aramis, we're going to go ahead and take a look at the questions. Are you ready for your first one?
Yes.
All right, perfect. So the question is, what computer language do you use when creating ROS packages?
When creating packages for ROS, you can use C++ and Python. Those are the two officially supported languages. However, there are also unofficial ports for Java, Lisp, and a few other languages if you're interested. I don't know them all at the top of my head, but
that's okay. That's enough to get us started. Thank you. All right. So here's the next question. What kind of computer or motherboard is on the autonomous agricultural robot?
On the agricultural robot, there's a RoboRio and also an NVIDIA Jetson TX1. The RoboRio is something we use in FRC, first competition, to control the robot, and it's being used to interface with all of the hardware, like the motors, motor controllers, along with a few of the sensors, and also to receive commands from the external driver station. It's what we use to turn the robot on and off. As for the Jetson TX1, it's a single-board computer developed by NVIDIA, and we're using it to run the packages written for the robot on the robot operating system and also handle some of the heavier lifting, like combining data from all the sensors and also doing things like localization or mapping. I wrote more about this in a blog post. It should be linked under attachments and links.
Great, thank you. Thank you. All right. Let's see. Here's another question that's come in. How do you compare ECL with the other languages you've learned? Were there any challenges that you encountered in learning it?
So I think ECL is really not too similar to most other languages I've learned because I don't have any prior experience in query languages, and I noticed that was a large part of ECL since it deals with large amounts of data. So I think that was a challenge in learning it, getting used to mostly the structure of it since it's really different from most action-based programming languages, I guess, since it's, for the large part, based on declarations.
Okay, thank you. So here's another question that's come in. What inspired you to work with HPCC systems and ROS? Is anyone else doing this?
I was inspired by my mentor to work with HPCC systems since there's not any others. Well, there's no one else doing it, so it would be good to create something that would allow who wants to do it easily.
All right, fantastic. I'm going to go ahead and take a moment and go back to your last poll question. The question is, what roles do you foresee HPCC systems filling in the field of robotics? So our choices were big data and autonomous control. 50% thought big data and 50% thought it would be both areas. So very interesting. That was a very good question. All right. Here's a quick question, Aramis, that came in. Is your library in a ROS repository? And would you be able to provide us with a link? We could probably put that in our blog if there is one.
So my package is in a ROS repository, and I'm planning on publishing it through GitHub and also through the ROS build farm. At the moment, I don't have a link. However, really soon I will have one, and I'll probably publicize it through my blog, which is linked here.
All right, fantastic, fantastic. And we'll work with your mentor to make sure that maybe we're able to take and put that out on the blog and make sure that we're publicizing that for other people. All right, Aramis, thank you so much. We really appreciate your spending your summer with us.